Good evening, sir. This is the group who will present about the process control of the clarifier in wastewater treatment facilities. Wastewater treatment is one of the fundamentals of all industrial processes. It can either be operated in batch or continuous. This paper aims to model a proportional integral derivative controller over an equipment in the wastewater treatment process, after which the stability of the controller will be assessed so that it can be safely implemented. For the process flow, influent is fed through a bar rack, where screenings are removed, and the remaining influent goes to the grit chamber, where the grit is also removed. The remaining influent goes to a primary clarifier to remove sludge, after which it goes to an aeration tank, where more sludge is removed and recycled back to the aeration tank. The remaining influent goes to a second clarifier, where it goes to a disinfection to produce effluent. For this paper, we selected the clarifier. Clarifiers are operated in batch, but the process considered will be done continuously. With this, it is necessary to model and control the process so that the feed input does not overflow due to the volume entering in the process. For transfer function, my colleague Charles Chen will be the one to explain this.
So here is the transfer function of the tank. So we set GF and GM to 1. So in order to get the crossover frequency, we use this formula. Phi equals arctan of frequency. So we set the W to negative 180 and we calculated the crossover frequency to be 1. Then using the equation below, we use this to solve the amplitude ratio, which was calculated to be 0.25. And then the ultimate gain of the system is the 4 and the ultimate period is 2 pi. So solving for Ziegler-Nichols PID tuning, Kc equals 0.6 and Kc equals 2.4 and Ti equals pi and Td equals pi over 4. So here is the frequency response of the transfer function when it is introduced to a step change of 1. So as you can see, the graph is still stable, and here is the frequency response when the Kc is 2. So here it is oscillatory, but it is still stable. So here is the frequency response when Kc is 4. So it is very oscillating and it is somewhat stable already. So when Kc is 4.1, the system becomes unstable. So here is the Bode diagram of the Zien-Chun system. So it is the Bode diagram is still stable because the values of the magnitude is less than 0. And here is the Nyquist plot. So the system is still stable because the loops do not exceed negative 1. So it is still considered stable. So for the root locus, the poles and zeros are all on the left side of the imaginary axis, which means the system is stable. But when the Kc reaches 4, the system starts to become unstable. So in conclusion, Ku equals 4, ultimate period is 2 pi, Kc is 2.4, Ti is pi, and Td is pi over 4. So the system is stable at Kc equals Ku, but unstable when Kc exceeds 4.1, as shown in the Bode, Nyquist, and root locus plot. So this is where we end our presentation. Thank you, Dr. Auresenia.